In this video, we're going to look at how Coulomb's law applies with ion-dipole attractions. First point is some ionic compounds don't dissolve in water, okay? So not all of them do. Some of them don't. The solubility of ionic compounds can be explained through Coulomb's law. Okay, and I have Coulomb's law down at the bottom of this slide here. F equals K, which is our proportionality constant, times the fraction Q1, Q2, those are the charge of our two particles, over the distance squared. Okay, so the important thing to see here on Coulomb's law is that the distance and the force are inversely proportional. Also, the distance is being squared, so that means as the distance decreases, the force is going to increase significantly. Okay, so the key thing here is the cation-anion attractions within an ionic compound are usually much stronger than the ion-dipole attractions. Okay, sometimes they are, sometimes they aren't. Okay, if they aren't, then it will be soluble. If they are stronger, then it won't be soluble. Okay, so let's take a look at these two examples. So we have magnesium and barium. Okay, now let's take a look at where these two are on the periodic table. Okay, so we're looking at magnesium and barium. So magnesium is right here on our periodic table, and then barium is down here on the periodic table. Magnesium has 3 energy levels, barium has 6. Okay, so barium is going to be a much larger ion than magnesium. Those valence electrons are going to be much further away from the nucleus. Because those valence electrons in barium are much further away, that means that there is going to be a weaker attraction between those valence electrons and the nucleus. Okay, it's going to generate a weaker attraction between the cation and the anion of our ionic compound. With magnesium, the distance between the valence electrons and the nucleus is much shorter, so it's going to generate a much stronger attraction in our ionic compound. So we have two forces at play here. We have our ionic bonds, that's between our cation and our anion, okay? And then we have ion-dipole intermolecular forces. So when we put our ionic compound into water, the water, which is polar, is going to try to rip our ionic compound apart. Okay, so if the ion-dipole intermolecular forces are greater, it will rip apart our ionic compound. However, if our ionic bonds are stronger than the ion-dipole forces, then the ionic compound will not be ripped apart and therefore will not dissolve in water. Okay, so this is essentially what I stated. So the forces work against one another through Coulomb's law. Okay, and again, the distance is the key part on Coulomb's law. One of the forces will be stronger than the other. So either the cation-anion attraction within our ionic compound or the ion-dipole forces. Magnesium hydroxide is not soluble in water, and barium hydroxide is, because for the alkaline earth metal hydroxides, the forces of attraction from ionic bonds decreases more rapidly than the ion-dipole IMF when moving down a group. So again, when we look at our periodic table, as we go down a group, we're adding energy levels. The atom is getting bigger, and those valence electrons get further and further away from the nucleus, okay, which will result in a weaker cation-anion attraction.